The goal of this project is to compare different CNN architectures for 3D and 1D pose estimation. And to do this, we are going to evaluate different accuracies at 1 or 3 rotational degrees of freedom. These images and the data that we're collecting or using was generated through simulations in Unreal Engine. And at the end, we're also going to touch base a little bit on k-fold cross-validation and how that could help us improve our model. So data generation in Unreal was a pretty straightforward process. In essence, what you have to do is create an array of either 1D or 3D angles that you would like to evaluate. And then after that, you apply the rotation to the object you want to study, and you take an image of that. So now what you have is essentially a feature, the image, and a set of labels, the angles that you're going to be predicted in our models. Here is just an example of the three RDOF or the single RDOF images and their shapes and labels. So for example, for the 3 RDOF, we see that there are 7,999 images. One had to get dropped because of blur. There are 3 labels, and the image dimensions are 244 by 244. Whereas the single RDOF has 5,000 images and 1 label, and same image dimensions. For this experiment, we have a pretty simple CNN model that is primarily comprised of convolutional layers and max pool layers. What convolutional layers do is they essentially gather spatial information and find features in that space, while the max pool, what it does is essentially brings up down the dimensionality of the image and makes it more efficient and simple for the model to evaluate, making it a little quicker and learn faster. The primary difference between the shallow and the deep model is simply the number of convolutional layers and max pool layers it has. The deep model has 2 more convolutional and 2 more max pool layers back to back. So essentially we want to see how the complexity of the model will affect generalizability and how that would affect performance. So for my model, I ended up using a custom loss function. It incorporates the angular difference and MSE. The angular difference essentially detects the smallest difference in an angle in the unit circle. This is important because, for example, traditional methods like the Euclidean distance would give us tremendous errors, or could potentially give us tremendous errors. For example, if we predict our position to be 359 degrees and the true is 1 degree, the Euclidean metric would tell us the difference is 358, when in reality the answer would be 2. So that would give us completely different answers and could make our model unpredictable and behave erratically. Here we can see the accuracy results for the training phase of the single rotational degree of freedom sets, and immediately we can see pretty high oscillatory behavior across all conditions and tolerances. I believe this could be due to the limited amount of data points in our dataset that increases our variability and in turn can lead us or the model to overfit. Overfitting could be mitigated by decreasing the learning rate. That's something I did not explore here for the sake of model comparison, but in the future this is most likely something that would have to get addressed fairly quickly. So now moving into the training set for the full degree of freedom, if we briefly compare it to the single degree of freedom results, we can still see a little bit of oscillation, but not as much. So we could benefit here as well from decreasing the learning rate, but generally speaking, these models are performing better than how they did on the single degree of freedom, which is a little bit surprising. Also, both deep conditions outperform shallow models, which is differs from the previous slide where the shallow model was actually able to outperform the deep. Here we can see the deep and shallow models being evaluated in a single and full degree of freedom conditions using the test datasets. So what this tells us is what is the smallest tolerance our models can have while still achieving 90% accuracy. So if we focus on the single rotational degree of freedom set, we can see that none of the models reach 50% accuracy over 50 epochs, which is a little bit expected. And another thing that is expected is the shallow outperforming the deep, because if we recall from the training single DOF slide, the shallow was able to outperform the deep in that case. Maybe because the deep just overfits and fails to generalize. That could be a factor. Now, if we move to the full degree of freedom set, we can see completely opposite behavior. Both models achieve 90% accuracy relatively fast, with the deep model achieving 90% accuracy within 3 degrees and the shallow model achieving 90% within 4 degrees. I'm going to touch on one more subject, and that is k-fold cross-validation. And that is a pretty powerful evaluation technique that can be used to assess performance of a model by essentially dividing the data set in k equal subsets or folds, essentially running the train test split multiple times and evaluating the model many, many times. To see if k-fold cross-val can actually help our model generalize better and reduce variability, we went back to evaluate the shallow single DOF model. Now, immediately we can see a lot less variability in our data, and we also see pretty good accuracy results in 25 epochs. We can see that with 1 degree tolerance, our validation set was able to achieve maximum of 76%, almost 77% accuracy, while achieving 98% accuracy at 5 degrees. In conclusion, we're able to see through these experiments that the deep model is able to perform better and capture more information for the full or the 3 RDOF sets, whereas the shallow model was able to perform better on the single RDOF set, showing that not necessarily a larger, more complex model will perform better all of the time. Additionally, we were able to see that the k-fold cross-val was able to successfully decrease the variability and in turn increase performance for the shallow single RDOF test, which previously we saw varied quite significantly across the complete 50 epochs. This does face a couple limitations though. For example, k-fold cross-val is quite computationally expensive, so it was a little bit hard for me to run the bigger data set, the 6 DOF models, with cross-val without it lagging behind. Also, we were limited by the number of data sets which were generated in a simulation, so that's something that could get improved. I also did not include any form of image preprocessing, which is very common in the CNN space. And going back to the reason why we did this experiment, our model was labeled pretty accurately. And in real life, that's not always going to be a scenario. So we need to work on a solution that provides us a model with large generalization. So one that could effectively perform pretty well in both the single and full RDOF sets.